Welcome to part 4 of our series on building hybrid cloud applications. Today we'll be discussing security concerns for APIs. Before we get into that topic though, let's briefly review what we've gone over in the prior parts of this series. In part 1, we showed how to quickly build an API utilizing existing business logic with Thriftly. Although today's video doesn't depend on the prior videos, we are going to assume some basic knowledge related to using Thriftly and building an API. If you aren't familiar with Thriftly, it would be beneficial to go back and watch part 1 of this series. In parts 2 and 3 of the series, we showed how to build a front-end client against your API using Angular and React Native. Throughout the series, we've talked about this idea of a hybrid cloud architecture. Here you see an illustration of that architecture. This is an especially useful setup for ISVs that have customers that want or need to keep their database on premises. Using Thriftly's gateway technology, you can build an API that is deployed to a customer site and accessible on the internet without having to worry about things like network configuration, network address translation, firewall setup, and even TLS encryption, things like that. Thriftly can handle all of this for you, which allows for a setup where the front end of an application can be hosted in the cloud, while the customer-specific API is hosted right out of their own facility. And I'm going to be using this term hybrid cloud application or architecture quite a bit in this presentation. When I do that, I'm referring to this sort of split setup that you see illustrated here. This presentation on security is going to be a little bit different than our prior presentations because I won't be directly showing any running applications. Instead, I'll be looking at security more at a theoretical level and going over things like best practices. First, we'll go over the idea of the onion model, and then we'll be spending quite a bit of time looking at some pseudocode that illustrates some common pitfalls to avoid as you develop your API. I'll focus on the idea of how to think like a bad guy when analyzing your own code. After that, we'll debunk the idea of perfect security and look at strategies to deal with the ever-changing minefield of security exploits. Finally, I'll take a brief look at how some of what we've learned applies specifically to hybrid cloud architectures. So let's go ahead and get started. We all know that security is layered. We deal with it every day for most of us. Two-factor authentication, for instance, adds another layer of verification to the authentication process. But very often, developers take a one-size-fits-all approach to security. They figure that they're going to use industrial-grade encryption with these huge 4096-bit keys, and that's going to provide such a strong layer of security that they can ignore the rest to a large degree. But really, all the layers here are important. If you're encrypting a system with a crummy authentication system, you still have a weak security architecture. If you have a rock-solid authentication system but don't use encryption at all or use it incorrectly, well, guess what? You probably have an even weaker security architecture. That doesn't necessarily mean, though, that a weakness in any of the layers spoils the entire onion. Notice that at the core of the system here is your business rules. So let's take the case of a back office software package for medical billing. Because this software by necessity has to deal with social security numbers in the United States, that could definitely be a concern. So a business rule you might have in place is to never return the social security in a data query by default, or allow a query that returns a set of data containing or sorted by social security. So you could still verify someone's social security number. They could give you their SS number, you do a find on it, and if it's found, you can return the data record, but a find on any other piece of data will only ever return a record without their social security number. Well, this is a very strict business rule coded into the core of the software. You could have a weakness in the rest of the layers of security, but because of this very strict rule at the core of the software, you can at least have some assurance that any leaked data by your API won't contain the social security number. This is the sort of security that you need to consider as you build your API. Now, for a very long time, developers have thought mostly about solving problems or what makes things easier or more productive for them. Decades of development have this foundational concept of trust, very similar to the lock on your front door. You lock your front door, but really that's to keep people from just walking in opportunistically. If someone wants into your home, well, they can pick the lock or they can just break a window and get in. To find a really secure home is actually pretty rare. Part of the reason is that in general, those that want into your house are actually pretty few and far between. But this analogy of a locked door doesn't carry over into the world of data security. Yes, there are opportunistic data thieves, those who will take something if it's just sitting there for them to take with little or no effort. And a simple lock could keep those individuals out. But protecting against the myriad of automated tools that try to exfiltrate data from your system and the endless supply, it seems, of script kiddies trying to delete the data on your server just for fun, it requires thought and planning on your part to protect against those things. Then there are those bad actors who actually have a vested interest in using the data that's socked away in your database. Very often, they're not interested in your application data. They're after those login credentials, hoping to use those to get to more easily monetized data, like credit card numbers that are stored in other sites, or logins to store sites, or banking logins. What this means for you, for developers, is that you have to stop thinking about your application in terms of how you build that application for trusted local users and start thinking like a villain. Things that were features in your Windows application could end up being exploits in an internet-facing API. These security risks could come from laxity, such as a developer doing a quick and dirty fix by dumping more data than they actually need into a structure, not realizing that private data is being transmitted. Or it could be due to overconfidence related to the use of a framework, not realizing that access outside that framework could be put in danger. What we're going to do now is look at some innocuous looking API calls and see if we can think like a villain to see how these APIs could be abused or exploited. So for our first example, what we have is a published API call with some pseudocode that's meant to get the product details for a public-facing store site. Now, the developer realized that the data he wanted was available already in an existing API call, or in an existing function call that he had access to. A call to item record is going to return the product details as shown in the structure on the right here. There's nothing too suspicious at first glance, but there are a couple of things that stand out when you start to think like a villain. First, we see that our structure, which has the data elements that the developer is interested in, contains not only the price and description, it also contains the cost. Now, for most companies, this is a proprietary and private piece of information. What happened here is that the developer saw the data that he needed and used that call the same way he would put fields onto the screen of a Windows application. He's just not going to show the cost on the screen, right? But since this is for a public-facing website, you have to consider every piece of data that's passed. Now, there's a second, less obvious issue here as well. Notice that Boolean in the structure there, the for purchase Boolean. Maybe that's used to stage items that haven't been released yet. But since we don't have any obvious check on that in place, if the ID, which as you can see for this is an integer, is guessable, you may be able to get the details of products that aren't even released yet. Now, you may think that nobody is going to attempt to do any of this on your application, but that thought process is just wrong. We regularly see all kinds of calls attempting to get at private data or to fuzz an API call to bring down a site. It's rarely due to things like corporate espionage. Normally, it's just automated tools or script kiddies that are starting small. Let's go ahead and look at another example now. This one is much more dangerous, and it's a unique danger to developers that are working on applications that originally used a record-oriented interface, such as Dataflex or the ISAM interface for btrieve, that are now using a SQL backend, but still have that record-oriented interface available. To start, we have this publish function that uses that ISAM interface to create a new customer record. It's pretty straightforward. Now, we can assume that there's a login routine that would return a token that you need to pass or a pre-shared key or something like that in place to protect this call. But we're going to ignore that authorization layer of the onion for now and assume that the user is authorized and authenticated to create a new customer. Now, we have here another function that's a bit different from the last. This one, which returns a set of data, makes use of embedded SQL. Note that there are no parameters passed from the API call that could be easily exploited in a SQL injection attack. So what's wrong here? Well, this one is a bit more esoteric than the last. Our problem in this case comes from two sources. There's the assumptions that were made in our prior function about that ISAM interface, and there's also a poor practice that's used in this function here. Our create function, if you'll recall in that last slide, made use of a record buffer to create a new row in our existing SQL-based table. A developer might do this for multiple reasons. The code might already exist. It could make use of validation that is embedded in the application logic rather than implemented in SQL. But also, they may know that this interface doesn't have a SQL injection risk associated with it since it's not using SQL, at least not at this level. Although that is true, there isn't a SQL injection risk at the time that a record is created. It doesn't mean that there is no SQL injection risk at all. You see, someone might come along and attempt to add our old friend Bobby Tables to your customer list. Now, they're not going to get anywhere right off the bat because, as we said, there isn't a direct SQL injection risk here. But by making that attempt, there is now a latent SQL injection attack sitting idle in your database. Bobby Tables is sitting there waiting for someone to call this cusp suspended with balance and activate that SQL injection attack. The problem in our second function is that the developers used string formatting for the SQL without any form of sanitization. Probably they saw no need to sanitize the data passed in since the data is coming from a record buffer, not from user input. Well, how do you go about fixing this? There are a couple of steps that you can take. One is to only use parameterized queries rather than building your own static SQL statements as is illustrated here. The second thing you can do in cases where that may not be an option is to make it a policy to always sanitize input from any data source, not just user input. All data sources would be sanitized. The key here is realizing that even when you're not using a SQL interface in a specific API call, you can't assume that other areas of your application are so constructed. Always sanitize your SQL and use parameterized queries where possible. We're going to look at one more example to drive home this idea of thinking about your code like a villain. For our last example, we're going to look at a case that involves almost all the layers of our onion model we looked at initially. One thing we see developers do on occasion is pass settings or privilege data through an API call. They may reason that the settings are just for reference in use in the front end and that they're going to reload the privileges on each call anyway, so they can pass them to the client and have the client pass them back to them. Looking at the example we have here, we see this save invoice call that's passed a privileges structure that contains limitations on what this user is allowed to do. Now, because we're dealing with a stateless system, this structure is passed down to the client at some point, and they pass it back with each call. The developer is correctly reloading the privileges so that if a client went in and changed the discount level in that structure, for instance, it wouldn't actually matter because we're reloading the privileges in the server backend anyways. In fact, this developer's even used a GUI for their user ID to make it harder to load someone else's privileges. But they've made one simple mistake here. There's actually a privilege escalation issue here. It requires that they get someone else's GUI'd, some other user's GUI'd. That may not be something that's easy to get, but it's not impossible to get. Imagine that this is a public API and someone's having a problem using that API. So they post the data that they're sending onto a forum asking for help, and they don't realize that they should have masked out their GUID. After all, you need to be logged in to do anything anyways, right? And it's not like the password is embedded here. So if I'm a user that's allowed, for instance, to give a 5% discount, but an admin user can give an unlimited discount, if I were to get the GUID of an admin, or possibly even the GUID of a template record that's used to make a copy of the privileges record, that might have a fixed GUID. I could pass that in the privileges structure here. And because there's no verification that I am the user associated with this privilege structure, it'll let me discount my invoice as much as I want. Now, there are a couple of causes of this problem. First, although they're doing an authorization check in this code, which is making sure that they have the privileges to set the discount that high, there's no authentication check. They're not the user associated with those privileges. Secondly, this method of passing metadata to the call about rights it's really the wrong way of doing it. It can be done using this method, but it takes quite a bit of work to do so. And as you can see, it's very easy for a developer to miss an important step like this. Instead, what you might consider using is a JSON Web Token, which is something that's built into Thriftly. JWTs have a single point of entry which handle both authorization and authentication on each and every call. Additionally, JWTs use cryptographic signing, which means that you don't ever have to recheck that what was passed to you, as was done in this example, was altered, because your API is going to be it's going to be verified for you before it even gets to you. Thriftly uses industry standard cryptographic techniques to make sure that the data contained within that API call, within that token actually, has not been tampered with. So if the client has a JWT that contains authorization data, you can be sure that when they pass that token back to you in a subsequent call, that it hasn't been altered at all from what was originally sent. There are so many other examples that we could choose to look at. We've just looked at 3, but the point is you have to look at your API early in the development process and consider if and how that API is going to be used and how it could then be abused. Consider who the users are. Do the APIs need to be truly public? Are the consumers of the API trusted? For instance, is it only going to be consumed by in-house developers, or are there consulting partners that you're dealing with? What kind of non-security abuse could you imagine? Mistakes by developers can often look like exploits. For instance, if they hit an API too often or pass in huge amounts of data, it can look like a fuzzing attack or a DDoS. One last point in this area is related to what's known as the attack surface. Part of your attack surface is your API. Every time you add a new API call or extend the abilities of a call, you're growing that attack surface. You want to try and keep that attack surface as small and tight as possible. It's good to think about the potential uses of your API, but building for things that aren't in use is a recipe for disaster. Those dusty little corners of your API are often where those bugs and exploits are going to be lurking. Only expose what's absolutely necessary. Now, let's say that you've done all of this. You've gotten as close to a perfectly secure system as is possible. Unfortunately, saying that can often lead to a false sense of security. Some developers might even have a foolhardy view of the security of their system. They look at what they've done to make things secure and imagine that they've thought of all possible scenarios. But as we've seen some from recent hacks, such as the Foreshadow or Bluekeep hardware-based attacks, wherever there is hardware, wherever there is software, there's always going to be attacks possible. So even if your code doesn't have any glaringly obvious security problems, it's still beneficial to consider how unknown security risks might affect you. How do you protect against the unknown? Really, there are a few techniques that can be used to provide some protection here, and we're going to look at two of them now: isolation and mitigation. Isolation can come in many forms, but the ones that I wanted to focus on are application isolation, data isolation, and network isolation. Application isolation involves putting services with different attack surfaces on different physical or virtual machines. So for instance, it's best to keep your API server on a different machine from your database server. Yes, it might mean more hardware and more maintenance, but if your API server has some exploit that gives an attacker access to the file system and the memory of that machine, what's to prevent them from siphoning off your entire database or corrupting it? This might be one of the reasons that we see waning popularity of products like Windows Server 2019 Essentials. Running everything on just one server is a dangerous play these days. And it's one of the reasons that the cloud is doing so well. It's very easy to allocate yet another server to handle a small task for which you may not even have a clear understanding of the security risks. The next area of isolation is related to something called dynamic data masking. Data masking normally refers to redacting or replacing real data for the purpose of having a test database. But in this context, we're talking about something a little different that's referred to as dynamic data masking. This is also involving redacting of data, but it's done on your actual database by the database server itself. So for instance, you may have an unprivileged account for your API that you use to access the database. If you have dynamic data masking turned on, then this unprivileged user wouldn't be able to access some columns in a table, for instance. This isolates the extent of damage possible if someone were to gain access via some other means to your database through that API. They can't see any of that mass data, even if they get full SQL access to that database. The last area of isolation involves isolating the exposed areas of your infrastructure from the rest. So, for instance, we regularly advise that people put their API services on a different physical or virtual machine from their database server, and to put that API server into a DMZ or demilitarized zone where it has heavy restrictions on what it can do. Thriftly can help here because our gateway servers allow you to keep your API server itself inside a private network with no direct public exposure. Now let's talk for a minute about mitigation. Once you've acknowledged that exploits will occur, no matter how diligent your efforts, you can begin to consider how to minimize the losses associated with a break-in. Ask yourself questions like, do I really need to store this piece of information? Is the value of this piece of data greater than the exposure that it puts me at for having that data in my database? For instance, if you're looking at some piece of PII, personally identifiable information, just as a way of doing a verification and authentication verification, for instance, you can hash that data rather than storing it directly, or even storing it encrypted. You're still able to verify the data when it's hashed, but you remove the risk of that data falling into the wrong hands. If you're a SaaS vendor, consider having separate databases per customer rather than partitioning data within the database. This isolates each customer's data, and if it's done correctly, it also reduces exposure to mass data theft. If you're not able to do this, consider enforcing row-level security to, in effect, jail a user within their own data set. Another way of limiting the scope of data exfiltration attacks is to set speed limits and size limits on your API. You could use something like Azure API management to do this. Thriftly also has some basic tools to help in this area. For instance, you're able to set the maximum size of data that an API call can send or receive, and you can also limit how long an API call can take to execute. But for more control, or if you need finer grained control, you need to use something like Azure API management. The final item here relates to how error messages are reported. Very often, developers want as much detail as possible, sometimes even including stack traces with their errors. The problem here is that errors are a source of leaked data. In fact, they can leak all kinds of data, including the structure of your tables, data that clients normally wouldn't be privy to, that's stored in structures internally, and even code implementation details. One way of balancing the need for detailed errors with the need for privacy is to put in place a system where the client gets an error ID that developers can do a lookup on to find a detailed report of the error. The downside to a system like this is that it can be complex to implement, and very often people go too far with it and report so little to the user that it frustrates the user's efforts to correct the problem. There are other ways of sanitizing errors as well that are simpler, but whatever you choose to do, don't leave detailed error reporting on in a live system. Now, if we take a look at everything that we've gone over so far and look at it through the lens of a hybrid cloud implementation using Thriftly, we'll see some advantages, we'll see some disadvantages, and there are some differences as well to keep in mind. One of the differences that you need to address in a hybrid cloud environment is to make sure to have a local firewall that is going to block local access to your Thriftly endpoints. The reason this is important to do is because that local access isn't encrypted, and therefore within your own network, things like passwords could be retrieved by doing network sniffing. This isn't the case when you're using our gateway connections, though, because we provide a front-end SSL connection and encrypt the traffic between your server and ours by tunneling it over an SSH connection. A disadvantage in some cases can be the need for more hardware to run Thriftly on a separate server from the database. Although this isn't a requirement, we strongly advise doing so. Of course, you have the advantage that you don't have to directly expose anything from your network to the internet. Our gateways provide a level of separation there, which is a big advantage. But you should still consider what physical access there is to the hardware running the DB and API servers. This is something you're protected against in a fully cloud-hosted environment. Microsoft, Amazon, and Google all provide very high levels of physical protection at their data centers. This is the counterpoint to use with people that are on the fence about moving their entire system to the cloud. For some, the disadvantages are just too great to overcome, though. And for those, a hybrid cloud solution provides a good balance here. If all of this seems a bit daunting to you, remember that Thriftly includes many features to make securing your API easier, including the ability to define a function as a login function and to tag functions so that they require authentication authorization before they're called. Additionally, we offer free security consultations to help you focus on the most important areas for your application. Our consulting teams offer application modernization services to help you transition your existing application to a secure cloud or hybrid cloud platform. If you haven't already, give us a call or send us an email for a free consultation. And thank you for watching.